Welcome to my tutorial on data types. We've already seen pre-existing types in Haskell, and hopefully you've learned a little bit about how they're important to Haskell and programming languages in general. Today we're going to learn even more about them, partly by creating our own types. Before we get into that though, let's talk a little bit about our favorite data type, lists. So lists, you've already seen them. It's hard to do much work in Haskell without them. They allow the grouping together of values using a special syntax that are these square brackets and each element separated by a comma. Set comprehension is a notation used in mathematics to specify sets in a dynamic sort of way. So usually it's done with either a vertical bar like this or some sort of like dot. And what you do is you specify the set with curly braces. Usually in math, we use curly braces to specify sets. And what you do is you specify what you call a generator, this part here. And you say that some variable x is an element of some other set. Okay? And then for each element in that other set, so this in this case, the other set would be 1 to 5, the set of 1 to 5. So for each element inside that set, you specify a new element, in this instance, x squared. So we could use this set comprehension to generate the set 1, 4, 9, 16, 25. Now, we shouldn't confuse lists as a data structure in Haskell to the abstract concept of sets in mathematics, even though there are some similarities to them. But just keeping in mind that they are different things. Just like there's set comprehension in math, Haskell has list comprehension for generating interesting lists. So this is an interesting tool. So that set comprehension that I just showed you in the previous slide could also be defined using a list in list comprehension in Haskell like this. The x with an arrow part, okay, is a bit different. So in mathematics, we would say x is an element of the set. Instead of doing element, we use this left arrow here. And this part is called a generator. Comprehensions can, interestingly enough, have multiple generators. So this comprehension has a generator for a variable x and a generator for a variable y. Let's try evaluating this list comprehension in GHCI. So we'll assign a variable and load it into GHCI. So make sure it's saved, open up a terminal, and let's load this into GHCI. .hs. Okay, and now let's run it. List. So the resulting list, you'll notice that it iterates, it starts at x and iterates through y. Okay, so it's like x is 1, so it starts at x at 1. Okay, and then the next element, it stays at 1, okay, and it's moving through y. And then when it gets through y, then it moves to the next element of x, 2. Okay, 2, 4, and moves through like this. Now let's say we change these generators around. Okay, make sure you save. And we can load this back into GHCI by typing :reload. And let's try evaluating it again now. So you'll notice this has changed the list because the positions of the elements of the list have now changed. Okay, so now we start with the same thing, 1, 4, okay, as we started before. But now we're going to move through the x's first, okay? So we're going to stick at 4 while we iterate through the x's, okay? So we start at 4 here, y stays at 4, and then we iterate through all of the x's before we move to the next y at 5. We can make our list comprehensions even more powerful by using something called guards. So basically, after writing our generators, like inside this list comprehension here, where we have a generator that generates a variable x, from 1 to 10, we put a comma, and we could write any sort of Boolean expression that uses our newly created variable. And if the expression evaluates to true, then it will be included inside of the list. If it evaluates to false, it won't be included inside the list. So this way, we could generate a list of even numbers by using the even function that only returns true when x is an even number. Another good example of this is if we wanted to find all the factors of a number n. So the factors of a number, I'll put this in a comma here. Let's say the factors of the number 6 would be all of the numbers, okay? Factors of 6 would be all of the numbers that divide 6. And we probably want to exclude 1. So 1 divides everything, so we could just exclude it. So 2 divides 6, 3 divides 6, 4 does not divide 6, 5 does not divide 6, 6 divides 6, but we'll also exclude that because every number is going to be divided by itself. And then, of course, nothing bigger than 6 is going to divide into 6, so we're done. So the factors of 6 would be 2 and 3. So what if we wanted to write a function that would generate this? So this is going to be a function that's going to take an int and return a list event. Okay, so how would we write this? So, well, we could do this with a list comprehension. So we'll generate x's, and x will come from the list of, so we don't want to start at 1, we'll start at 2 to x or n minus 1, okay? So we want to, these are all of the possible factors. We'll generate all of the possible factors of n, okay? So it'll be from 2 to n minus 1. And we'll say that n is a factor, or x is a factor of n, if n mod x equals 0. So what is this mod thing? So let's load up GHCI and test it. So let's save it first, and let's open up a new terminal. So I've shown you two types of division in Haskell already, and I'll refresh your memory on them. So there's fractional division. So this is division with floating point numbers. Okay, so this is division with decimal numbers. So that's just a simple backslash, the usual sort of division that you would probably figure you would enter into a computer. But then there's also integer division in Haskell. So this division will return the highest integer that gets returned. Okay, and now mod is a particularly useful operation. You see it sometimes in math, particularly in cryptography, but it's particularly useful in programming. And it returns the remainder of an integer division. Okay, so you can actually put it over, and it'll give you documentation of integer modulus. So this is actually the correct way you could formally define it. You see underneath integer modulus satisfying that equation. So to give you an example, 5 mod 2, what's this going to be? You guessed it, 1, okay? Because we try and divide 5 by 2, and it gets to 4, so it divides in twice. And then what's the remainder from there? 1. So our factors function, you could see something is going to be a factor of x. Okay, x is going to be a factor of n if x divides into it with no remainder. So I'm saying n mod x is going to equal 0. So let's double check that this works properly. Factors of 6. Yep, 2 and 3. Now, without further ado, let's talk about how to create our own types. So the first way I'll explain about how to create your own type is with a type declaration, okay? This is using the type keyword here. So I'll give you an example of a type that's actually already defined, the string type. So I've noted before that a string is actually just a list of characters, and it has special syntax that allows you to use the double quotations. So we go back to GHCI here. So a string, just to illustrate this, let's say we have, so remember characters, they need to be just a single character and they're put inside single quotes. So we could have the list of single characters, let's say AB here, okay? Could ask for its type. Okay, so this is a list of char, a list of characters. And you'll notice that this list of single characters can also be written using double quotations and just write the characters as is. Okay, so these are both the same thing. Okay, and just like I can specify that this is a list of char, there's a type definition in the prelude that was basically written like this: type string equals list of char, that allows us to use string in place of list of char. So another name for this is we would call this a type alias or type synonym. So we should note type declarations just give another name to something that already exists. So there really isn't any use for them except making your code more readable, your types more readable, which is not something that should be underestimated. We do want our code to be very readable. This is a very desirable thing when programming. So a good example of this is, let's say we had a library that was plotting stuff onto a 2D screen, okay? Like, let's say maybe this is a library for doing 2D animation. So we would want this idea of a position on the screen. So what we could do is we could use a tuple in this example of 2 ints to specify the position on the screen. And just to make things more readable, to specify what this tuple of 2 ints is, we can make a type and give it the name pause for position, okay? And then this way, we could define different positions. We could say, oh, we have an origin, okay, that'll be the middle of the screen, which will be 0, 0. And then we could have a function left that takes a position and gives back another position. Now, I mentioned this in the other tutorial. It's very, very nice to make it so that your functions it's very easy to tell what they do just by looking at the name of the function and its type signature. This is why we put type signatures in our code. So this function here, left, it's called left. It takes a position and returns another position. What do you think it does? It moves a position to the left. Okay, so even though this is just for making things more readable, you shouldn't underestimate it. It's actually a very useful thing in Haskell. Now, to make things a bit more interesting, type definitions can have parameters just like functions do. So we could create a type pair that takes a type parameter A. So note, just like with how I explained with polymorphism, A is not a type itself. It's a lowercase letter, okay? And it doesn't have to be called A. I could have easily written the same thing with type pair B equals the tuple of B comma B, or type pair, anything, as long as there's a lowercase letter. And in this way, I can have a pair type that I then provide a specific type when writing a type signature, when actually using it. So this way, my pair type, let's say I want to write a function mult that multiplies 2 integers together, given a pair of integers. Okay, so this way I would specify pair int. Okay, or I could have a divide function that divides 2 floats together. Or I can have a function that is polymorphic and doesn't specify the type. It takes any type, okay, A, and it creates a pair. It just basically puts that type into a tuple. It takes its argument and puts the argument twice into a tuple, so it creates another pair, A. Type declarations can be nested in that you can make a type declaration, let's say position, and then make another type declaration that uses that previous type declaration. Okay, as soon as you make a type declaration, that's just a type like any other type in Haskell. However, they cannot be recursive. So we'll get into what I mean by this in the next tutorial coming right up. Okay, but since I'm introducing type declarations to you now, I should mention right now that you could not do something like this, where you declare a type tree, and then in its own definition, you use that same type tree. Data declarations are another way of defining your own types, but they're more powerful in that they actually let you create your own values. So type declarations, they don't create new values of any sort. They're just another name for a type and values that already exist. Whereas data declarations, they don't just create a new type name, they create new values that are associated with that type. So for instance, if we wanted to look at how bool is defined in the prelude, so the type bool that we've been using all along, it's defined in the prelude, and it's defined using the data declaration, data bool equals false, and the way I like to read this is or, okay, you use this vertical bar, true. So basically, you specify all the values you want to be included inside of your data declaration, separated by a vertical bar. Let's run through an example where we would want to create our own custom data type and not just use one that was already put into the prelude. So let's say we're having a program that answers questions, okay? But the standard true or false answer to the questions aren't going to quite cut it. Let's say we also want to have the option for a third answer of just, I don't know. So we can create a data type, data answer equals yes, or no, or unknown. And make note here, okay, these are values that we're creating, okay? So they need to begin with a capital letter, just like the name of the type answer needs to begin with a capital letter. And let's put this to use. So we can create a function, or let's just create a list, sorry. Answers and answers are going to consist of these three values, yes, no, or unknown. Okay, so we can go around and use these as values. Sorry, this is answer. Use these as values, just like we would use any other value, like true or false or 1, 2. And we can create a function, flip, that takes an answer and returns another answer, okay? And basically what this is going to do is flip will always just return the reverse of whatever answer you're giving. So if you give yes, it'll give back no. If you give no, it'll give back yes. But if you give back unknown, it'll just stay at unknown. So the way we can define this function is using pattern matching. So we'll, instead of writing like flip x equals something, instead of writing x there, we'll just put the value itself and define what the function will equal at that value. So for yes, it equals no. For no, it equals yes. And for unknown, it equals unknown. That's a little neat example. Let's try another example. So we can just get rid of this. Let's say we're creating a library that has to deal with different shapes. So we can create a data type for shapes, and it could have values circle or rectangle. But here's the thing. Let's say we want to specify the size of the circles and the rectangles. So we can give these values parameters, okay? So for a circle, we would want to specify its radius. So we can give it one parameter. So to do that, we'll put a parameter here, and we're going to have we're gonna have to use another type for the parameter. So what would we want to represent the radius as? We could do an int, but I think it makes more sense to do a float. And then similarly for the rect, we're going to want to specify the width and the height. So we'll give it 2 parameters. So we'll put space float, float. Okay, so the way we would represent this now is we could have a square. So like the unit square would be equal to the rect of 1.0, 1.0. So this is how we would have values of rect here. Okay, so when we make the data type, we're saying, okay, this data type shape. So this is a thing of data of type shape. So this data type, it'll have name shape, and its values will be circle with a floating point value attached to it. Or it'll be a rect with 2 floating points attached to that. So similarly, if we wanted to find the unit circle, that would be circle 1.0. Okay, and we could define helper functions for this. Say we wanted to define a function to construct a square. We could define a function square n equals rect n. So then this way, instead of having to write rect 1 here, we could just write square 1.0, and that'll construct a shape for us. We could even define more interesting functions now. Like let's say we want to define a function that calculates the area of a shape. So this will take any shape, so that will include a circle or a rectangle, and it will return a float for the area. So the way we could define this, again, we could use pattern matching. So there's 2 scenarios that we could match off of here. We could have a circle, okay, and that circle will have some float attached to it. So what we'll do is we'll leave a variable, we'll call it r for radius here, that will be the float that's attached to it. And we'll say the radius of a circle, if you guys didn't know, is pi times r squared. So the pi is a variable defined in the prelude that's equal to an approximation of pi. So like 3.14, blah, 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 blah. There's no point in memorizing beyond 1.4. And the other scenario is we have a rect, okay, and there'll be the width and the height of the rectangle. So we'll create 2 variables, w and h, that will represent these 2 floats here. And the area of a rectangle is going to be the width times the height. Okay, so this way we can calculate the area of any circle or rectangle given to this function. A really interesting thing to note about the values circle and rect here, when they have a parameter attached to them, is that they're kind of functions on their own. So if we load up a terminal, make sure this is saved, and load this into GHCI, okay, and we ask it for the type of, say, a circle 1.0. This is a shape, okay, that makes sense. In the same way that if we asked it for the type of false, it's bool, right? But what if we asked it for the type of just circle on its own, and we don't give it the float that's attached to it? Well, circle is now, see, this is a function type signature, something that takes a float and then returns a shape. Similarly, if we ask it for the type of rect, this is a function that takes 2 floats and returns a shape. Interesting, eh? One more thing I want to mention about data declarations before we finish off is, just like type declarations, they can have parameters attached to them. So consider this type maybe that has a type parameter attached to it. So maybe it could either be nothing or just whatever type is attached to it. So instead of, so jest is a kind of function, just kind of like rect and circle were functions that returns a value of the type maybe. But unlike circle and rect that had a specific type attached to it, float, jest is going to have any sort of type attached to it. And whatever type it does have attached to it will reflect on what the maybe type itself is. So consider, for instance, if we wanted to define a function safediv that instead of crashing when it tries to do division by 0, it returns nothing. So it takes two integers here, and if the divisor is 0, it just returns nothing. And if it isn't 0, it can't just return the int in this case, because it needs to return the maybe type, right? So it returns just and then the int inside of just here. And then we could define functions to pull that integer out if we wanted to by pattern matching. So for instance, let's say we have our function safediv. So we could first define a function to tell if it returned nothing or just. So we could say is just, and if is just is giving nothing, it returns false. And if is just is given just anything, so remember we can put this x or this underscore for anything, equals true. And then we can define, let's say, a list comprehension div from 10, okay? And it takes an n, and what it does is it'll be a list comprehension of safe div 10x, okay? Where x comes from n dot dot, let's say 50. And then what it does is it's going to check if is just safe div (10x). So this is a weird thing. So it's going to use safe div here. Oh, and I need to spell it correctly. Actually, safe div. So it's going to use safe div here. I can put this on a new line so you can see it. So it's going to create a list of maybe int. Okay? But what it's going to do is it actually has this guard here to be like, well, only include it if this result of safe div is a just, right? And then what you could do is after you know because you did this guard here to tell that it's just, after you know this, you could define a function, we call this from just, okay? Where if it's nothing, then it throws an error. But then from just x here, okay, is going to return that x. Okay, and then we could change this function. So right now, this will return a list of maybe int. So it's gonna basically return a list of just a bunch of like just this, just that, and so on. So let's say we want it to actually just be ints, because now we know, because we're doing this guard, we know it's only going to return things that are just and never return a nothing. We can map from just over this list. So this is an instance where we've kind of circumvented ever having to throw an error like this, okay? We're able to be like, well, we'll define the safe div that if division by 0 happens, it returns nothing instead of actually doing the division by 0. And then what we do is we filter out all of those instances, okay? Because now we have this kind of wrapper around bad things that happen. And then we pull things out from that wrapper. Okay, I'm calling it a wrapper. You could also consider it, the maybe type is kind of like a box, okay? Where it's like, it has a label on it, of being nothing or just something. And you can put the actual values that you're concerned of inside of it. So this is a bit of a this is a very interesting trick that I find that I think in Haskell. The other interesting example that we could do of this is if you remember at one point I mentioned how to define the function head takes x's or returns x. And I mentioned that the type of head, it takes a list of A and returns an A. And I was mentioning, okay, but what happens when head gets called on the empty list? So this pattern, it doesn't match the empty list. So right now, if you give head the empty list, it'll just throw an error. So what do you do in the case of the empty list? What do you return? And we're just kind of left being like, there's nothing to return. Well, what you could do is just like with safe div, you could define a function safe head. Ignore the obvious double entendre here. Safe head here, and it'll either return a just at or nothing on the empty list. But it involves changing the type signature to maybe A. Okay, and now this way, whenever you perform head on a list, okay, let's say we load this into GHCI and we try out safe head here. Okay, we try safe head of the empty list. It gives nothing. Safe head of 1, 2, 3, and it gives just 1. Okay, and if you wanted to use that, you would have to use that actual value 1. You would have to pull it out of the just, right? So you would have to write a function that pattern matches on it and then takes it out, like the from just function that we defined before. So last time I showed you the data keyword for constructing types in Haskell. Whenever we construct a type using this data keyword, we refer to these as algebraic data types. So just in case you hear this somewhere else, all you need to know about algebraic data types is that these are data types that are created using the data keyword in Haskell and not just the type keyword. So there's two parts of algebraic data types that we really need to take a good look at. So one is the data or type constructors. And really all this means is the type name you're giving your data. So the first thing you do when you write a new data type in Haskell using the data keyword is you give it a type name. So this is going to be the name that's used in your type signature. So like, let's say you have a function sumfunc and it returns a type of your new data type. This is what you're going to put. This name, this first thing is what you're going to put as the type name. The second thing we should be aware of are the value constructors here. So a value constructor is going to make the values associated with your type. So let's say our type name data type here, our sample data type here, it has two value constructors, val1 and val2. So val1 creates a value all on its own. So if you just write val1, that's already a value. Val2, in order to construct a value, needs to have an int attached to it. So val2 only actually becomes a value on its own when you give it an int. So if you write like val2 5, or let's say you have some variable and you write val2 and you attach that variable to it. Now this val2 attached with the variable becomes a value. Just on its own, it's just a value constructor, which you could think of as being like a function that takes an int and returns a type name. Let's try out a more specific example of this. So let's say we're trying to create a data type that's going to keep track of different students. So we'll call it specifically student ID. So student ID is going to have two strings attached to it. Okay, and it's going to have, let's say, the first string will be your McMaster ID, MID. And the second string will be your student number. So we'll pattern match on both of these things to pull them out. Okay, so we've created a data type student ID, and what we've done is we've made, this confuses a little some people at first, but we've made the value constructor student ID here the same thing as the type name. So it allows you to do this because whenever you write a student ID inside of a type signature, it knows that you're referring to the type name. Whereas if you write it in outside of a type signature, like let's say for pattern matching purposes, then it knows you must be referring to the value constructor student ID. Okay, so student ID is a value constructor that has two strings attached to it. So we can pattern match onto it and be like, well, the first string here, we'll write a function for it, map ID, that returns it. And now that we've written this function here, anybody reading this code can kind of figure out, okay, the first string that's attached to it, that must represent your McMaster ID. Whereas the second string, we've written a function student num that pattern matches and pulls out the student number. So now we know, okay, this second string that's attached to it, anybody reading this code could tell, well, we must be reserving that to represent the student number because of this function we wrote. Now, a shortcut, we often do this when we create data types that have value constructors with different types attached to it. We write these functions to pull those types out of the value constructors. So a shortcut we could have done for this, we could have written this a different way. So instead of writing it, so I'm going to comment all of this. And actually, I'll use a multi-line comment to do this. So the other way we could have written this is data student ID equals, and then we would write the value constructor name, and then we would put curly braces and we would put Mac ID string student num string. Okay, and this is actually, this right here is actually just a short form, a special syntax for all of this code right here. Okay, and this way we could look at this and be like, okay, we have this student, oh, and sorry, this should be student ID to be the same thing as what we wrote up here. We have this student ID value constructor, and it has two strings attached to it. And we can be specific about what we want these two strings to represent. We can be like, well, this string represents a Mac ID, and this string represents a student number. Okay, and these two things here will act as functions to pull out the student number and Mac ID, respectively, of the string. So let's make an example student here. Okay, Jimmy, and he has student number 0001. Okay, so we could save this, and let's load it into GHCI. Okay, and what we could do, so remember, let's say we try and write student num, we get an error right now because it has no way of showing student one here, right? And we want to be able to show our data type, any data type that we create, we have to put this deriving show underneath. Make sure you save, go back, reload. Let's try that again. Okay, so now it can show, and it's saying this is a student ID with Mac ID equal to Jimmy and student num equal to 0001. And let's say I say Mac ID, I use this as a function, student1, See, now it returns Jimmy. Similarly, if I do student num, student one, student num, student one, it returns the student number of this. So let's do one more example of this. Let's say we have a university ID. So let's get rid of this code now. Let's create a data type, university ID. And this data type is going to be a student ID with Mac ID, string, student num, string. Or, so this is going to be a more generalized form of what we were doing now. So instead of just having IDs for students, we're also going to have a faculty ID. And a faculty ID is going to have a Mac ID, string, a faculty num, string, and a salary float. Okay? And now we can write a function over this type. Let's say a function det that takes a university ID and returns a float. And the way we could calculate the det, let's say if you're a student, regardless of who you are or what your student number is, you're in a bunch of det. Whereas if you are a faculty, let's just write faculty ID here. So we won't bother pattern matching on faculty ID, and we'll make sure to put it underneath student ID here. Okay, so that we know, well, if it makes it to this case here, it must be a faculty ID, because student ID and faculty ID are the only two value constructors here. So just write a variable here, faculty ID is going to be equal to 2 times the salary of faculty ID. So we're writing salary, okay, the salary here, to pull out whatever the salary is attached to the faculty ID here. And we can make a few examples of this, some few test cases. So let's say we have student 1 is equal to student ID. Let's make the same student as before, Jimmy. 1. And then we'll have prof1 is going to be equal to, so we're going to have a Mac ID, a faculty num, and a salary. Faculty ID. So the Mac ID is going to be me, Curtis. Now we need a faculty num. And salary 2. Oh, and this isn't a string. This is a float. Okay. So let's save this and let's reload it. And we can try out det of student 1. Okay. It writes this in a short form, 1.e to the 12. So this e to the 12 means 1.0 times 10 to the power of 12. Okay, so it's this number. There must be 12 zeros here. Okay, this must be 12 zeros here. And let's see the det of prof1. Well, prof1's det is a lot better than the student stat. And you'll notice both of these things are university IDs, even though even though one is a student and one is a faculty, these are both under the same type. Okay, and that way we could have one function that takes both of these things as an argument. So last time I gave you an example of a recursive type for defining the natural numbers. So this was a type that used itself inside of its own definition. And we needed this type to be recursive because this is a type that was going to have an infinite amount of values associated with it. So we wanted to define a type for the natural numbers. So these are any positive whole numbers, including 0. Okay, this is a type that would have to have an infinite amount of value. So we couldn't just keep writing that data nat equals 1 or 2 or 3 or 4. We couldn't just keep doing this over and over and over again. We needed some way to specify that, okay, this is how you generate new values of this type. So we used recursion to do this. So another good example of this is if we wanted to redefine the list type that already exists inside Haskell. So to take a look at this, let's recall an example list, call this list 1. It goes 1, 2, 3. And then we have list 2, okay? If you remember, I pointed this out, this is just special syntax for 1, 2, 3, empty list. Okay? So this is just special syntax for this. We could say that this is the true way to represent a list inside of Haskell. Okay? Now, the interesting thing to note here is that this colon and this empty list here, these can be considered value constructors for the type list. So we could define this in our own way. Let's say we want to define our own list type in Haskell. So we can say type, there's our data, and we'll call this int list. We'll restrict it to being lists of only integers for now. Int list equals, and then what we'll do is instead of having colon here, we'll create a value constructor that would correspond to what colon does in the default list called cons. And the way cons would work is cons would take an int. Okay, so the first part is an int, and the second part is another int list. Okay, so cons takes an int, so it takes an element of the list, and then another list. Or empty. And empty here is going to correspond to these two empty brackets. So the same way that we wrote list 2 here, now we could write this in our own custom list. So we'll call this custom list equals cons 1, cons 2, cons 3, empty. Okay, so we've essentially accomplished the same thing. So this is our own list now that we've encoded in our own way using a custom data type that we defined. And if you were to look inside the prelude at how lists are defined, it's roughly defined in the same way, but it uses some special stuff to write colon here instead of cons. Usually you're not allowed to write colon as a value constructor. It needs to be something that begins with an uppercase letter. But just ignoring that fact, you would define lists basically the same way. Okay, where cons here would be this colon, and empty here would be the empty list. Now, the one other thing besides the difference between cons and the colon and empty list and the two square brackets that separated our custom list from the built-in list in Haskell is the fact that the built-in list in Haskell can work over any type, whereas our custom list that we just defined only worked over ints. So to rectify this, we need to use polymorphism. So a polymorphic data type is going to be a data type that takes a type parameter. Okay, so we know this is a type parameter because it begins with a lowercase, and it's kind of attached to the type name here. And it's going to take this type parameter, and this type parameter is essentially, it's like a placeholder for any type. So now this way, instead of specifying specifically that, oh, this was a int list, now it's a list of whatever type A. So if we were to look at how we could redefine this now, instead of writing int list, so let's change the name of it too. Now it'll just be list of A equals, and then instead of putting int here, we put our placeholder a. Okay, and now there's also a bit of, this is a little bit of extra complication that we need to make note of. Instead of just putting int list here, so first of all, we'll change it to our new name list, but instead of just putting list here, we need to specify, no, it's not just a list, it's a list of a, and we put brackets around it to let it know that this is one thing with cons. If we didn't put brackets around it, then it might look at it being like, oh, cons takes three things. It takes an a, some name list, and another a. No. We put brackets around it to be like cons is attached to two things, a and another list of a. Okay? So now you would notice, so our custom list here, in the same way that we write this as being a list square brackets of integer, now custom list here is a list of integer. Okay, and we could have had another custom list. Let's say a custom list 2, and there's going to be a list of, you guessed it, bool. Okay, so now we've made a polymorphic data type. It's polymorphic, just mean it could be many types. Whenever you hear polymorphic, just think of many different types. Now that we're starting to learn more about data types, now is a good time to bring up the case syntax. Okay, so we've been using pattern matching already quite a bit, in a way that whenever you define the function, you're saying the function, instead of putting a variable for the parameter, we put the actual value and then say, well, this is how the function is defined at this value. And then we just write kind of multiple function definitions where we match for each value. Like this. So another alternative syntax for doing this is we write a function like usual, and we give a variable for the parameter, and then we write case, the variable we want to pattern match over of, and then we write each different instance, so each value we want to pattern match to, and we use this arrow to specify what we're going to return at that value. So these two functions are defined exactly the same way. And now the case syntax is particularly useful because sometimes you do want to pattern match over a variable, but you don't want to do it inside of the function definition exactly. A good example of this would be, let's say we have our safe head function from before that takes a list and returns the first element of the list, but instead of just crashing, if you give it an empty list, it returns nothing or just the thing in the list if there's one thing. So let's say we have a function first of, and it takes two lists, x's and y's. And what it's going to do is it's going to put those lists together, and it's going to take the first thing from those lists. So we want to use safe head to do this. So we would say x's safe head of x's plus y's. So this way, like let's say x's is the empty list, then instead of returning the first thing of x's, it returns the first thing of y's, right? But if x's and y's are both the empty list, well, then it's just going to return nothing, okay? But let's say we don't want this to return maybe a. Let's say we want this to return a and then crash otherwise. So what we're going to want to do is we're going to want to pull out the value from Jess. Okay, we're going to want to pattern match here. So a good way to pattern match without having to find a whole nother function just for pattern matching is we could write the case expressions. We'll say case of, okay, and now we'll write, so what are the two cases here? It's either going to be nothing, and then we'll throw an error, okay, first of two empty lists, or if it's just x, okay, then we'll return just that x. Let's finish up by talking about pattern matching on lists in particular. So with our new list type, we could have written a pattern match for this by pattern matching on the cons or empty list. So we could write a function that pattern matches on cons. It would be cons, the first thing in the list, and the rest of the list, or the empty part. And this is the same in Haskell as writing func x colon x's and func empty list. So to emphasize this, delete this here. Let's write let's rewrite the function map. Okay, let's write our own map. Call it custom map. Okay, so if you remember the map function, it takes a function from A to B, a list of A, and it returns a list of B. So what it's basically going to do is, let's say you have a list of 1, 2, 3, and you want to go through that list and you want to add 1 to everything in that list. What you could write is you could write map 1 plus 1, 2, 3. Okay, and this would return the list of 2, 3, 4. Okay, so custom map, it's going to take a function, we'll call it f. So f here is going to be our function from A to B, and some list x's. And what it's going to have to do is it's going to have to move through our list x's and apply the function to every element in the list. So how are we going to do that? So let's start off by pattern matching. So let's start off by just saying, well, how would we apply f to the first element of the list? So what we could do is we could pattern match and be like, well, instead of just putting x's here, we'll have the list x colon x's. So now x would be the first thing of the list. Okay, so in our example here, remember this list 1, 2, 3, this is the same thing as writing 1 colon 2 colon 3 colon empty list. So when we write this pattern match x colon x's, x is 1 here, and 2 colon 3 colon empty list is x's here. So x's is a whole list, and x is just one element of the list. So to start off, what we're going to do is if we want to just apply f to the first thing in the list, we're just going to apply f of x. And there we go. Now, the trick here is now we have to move through the list x's and apply f to every element in that list x's. So we need a function now that takes f and applies it to everything in the list x's. But of course, that's what we're doing right now. That's the function we're making at the moment. So what we're going to do is we're going to have custom map f of x's. So we're just going to call the function again on the rest of the list x's. And now what we need is some way to put this together with the rest of this list. So what's happening is this is going to be one element now. Let's put this, we don't have to put this in brackets, but let's put this in brackets just to be super clear of what's going on. So f of x is going to be one element, and custom map f x's is going to be the rest of the elements. So how do we put these together? Well, that's exactly what this colon does. This colon takes one element and another list, and it puts them all together into one list. So we're just going to put a colon here, and we can put this all on one line. Okay. So now this is the recursive case, okay, that we have going on right now. What else do we need? So right now, this will go on forever. Well, actually, what it'll do is this will keep going until this pattern doesn't match anymore. When does this pattern not match anymore? When you get to the empty list. So eventually you get to the empty list, and then you can no longer match it to this pattern x colon x's. When you have the empty list, like say the empty list right here, eventually x's becomes the empty list here. Like when you get to 3 colon empty list and you pattern match to this, then x's will be the empty list here. And then there's no colon anymore. Nothing to pattern match there. So what we need is a case now of f empty list. Okay, so this will be our base case, we would call it. And what do we return in the base case? So let's kind of like walk this through. Like if we were to evaluate this, let's say we're going to call custom map 1 plus 1 colon 2 empty list. So it's just a list of 1, 2. So what does this get evaluated to? Let's move through it one step at a time. So we're going to sub this in. So 1 colon 2 colon empty list is going to pattern match to this, where x is 1 and 2 colon empty list is x's. So we're going to have 1 plus 1 colon custom map f2 colon empty list. Okay. So now we need to, let's forget about this part for the moment. Now we need to do the same thing, but on this part here. So what does this match to? So custom map is going to match to, let's say 2 colon empty list is going to match to x colon x's here. So now this is going to be 1 plus 1 colon brackets. So now this time f of x, so 2 is going to be x here. So this is going to match 1 plus 2 colon custom map, it's going to be called again, f. And now x is here is going to be the empty list. So the empty list here. So now we need to decide, all right, what should this evaluate to finish up this list? Well, whenever we have a list like this, where it's like 1 colon 2 colon whatever, what does it always end up ending with? The empty list. So when we get to the empty list, we should just return the empty list. Okay, and now that'll finish this evaluation. 1 plus 1 colon 1 plus 2 colon empty list. So of course we'll turn into 2 colon 3 colon empty list, which is just another way of writing the list of 2, 3. So this pattern here of moving through lists, whenever you want to move through a list and do something one at a time on that list, you can always use this pattern of matching on x colon x's, doing your thing, making a recursive call on the tail x's here, right, on the rest of the list, and then just keep going until you get to the empty list. So this is a pattern we use all the time when writing algorithms on lists.